Alright, hi everybody. Today we're going to do a short little video on testing for heteroskedasticity in Stata. So before we start, apologize, I still have a cold, so sorry about the audio again, and sorry about the glare shining off my big white board back here. But heteroskedasticity, that's our topic of the day, so let's go ahead and do it. We're going to follow along with a previous example. So we're going to use some cross-sectional data on wage and education. And again, this data really handy, is made available through Boston College. It's an example data set from Jeffrey Wooldridge's Econometrics textbook. You don't need the textbook to follow along here, however. We'll walk through the whole thing. So what makes this, again, particularly useful is that we can grab the data right from that website without opening it up in Excel and importing it, etc. So we can use that bcuse command. So that's, again, the Boston College data grabbing tool. You have to install that ahead of time. And we're going to, again, use that data file wage1. So again, we have all the tools here to estimate a wage determination model. And yet again, we're not going to go through the specification process in total here. And obviously, we're not going to get the right specification, but imagine we were estimating a fairly simple model here, regressing the level of hourly wage as a function of individual level education, work experience, and then say we're trying to test for gender-based wage discrimination. So we have a female equal to 1 dummy variable. And we estimate the model, and everything looks good, right, so far. And for some reason, my Stata is very slow, waiting for it to catch up. How you guys doing? Having a good day? Fantastic. There it comes. Okay, so we've got our return to education, about 60 cents per hour of additional wage per year of education, highly significant. Every year of work experience adds about 6 cents to your hourly wage. So about 1/10 of the value of that year of education. So yet again, stay in school. And then unfortunately, we do have a negative and highly significant coefficient on that female dummy variable. So holding education and experience constant, females earn about $2.15 less per hour. But before we make any kind of real conclusions from this model, we want to make sure we can trust the results, right? So the first thing we think about when we're running cross-sectional data, in addition to potential endogeneity, think of other omitted factors that should be included. Once we've got that down, we want to make sure we can trust those standard errors, t-statistics, and hypothesis testing results. And what can push us off the rails there is that heteroskedasticity problem. And part of the problem is, looking at the results we see here, right, there is nothing at all to indicate whether or not we have heteroskedasticity. So we've got to open up the hood and know what to look for. So a good place to start, right, is to do, yet again, that old eyeball test. Let's just take a look at the results that matter and see if they conform to our kind of Gauss-Markov classical assumptions. So here with heteroskedasticity, of course, we're thinking about the variance, the dispersion of the error terms. Is it constant across observations? So a good place to start is just to pull up those residuals. So let's predict u hat, comma, residuals, comma, resid, just comma r if you want. And then we can just do a simple scatter plot. So a two-way scatter plot of these predicted residuals versus one of our x variables. So if you recall, when we think about heteroskedasticity, oftentimes there is a specific causal factor, right? A scale or proportionality factor that's going to drive those error variances to increase or decrease. We might reasonably suspect that as education increases, right, naturally the level of wage is going to go up, but perhaps the dispersion, the variability of wage increases as well. Right? The example I always use, right? You could have 20 years of education and have a PhD in economics, and your wage is well above the mean. You're way in the right-hand tail. Or you could have a PhD in art history, and you're way on the other side. The variability increases as education increases. Right? Let's see if that's actually true here. So we bring up our plot, and this This, of course, is the reason I use this data set, because this is the picture-perfect example of heteroskedasticity. So if we, I was like draw my graph, start the graph editor, Control L here in Stata, and we see this widening dispersion pattern, right? As education increases, the variability of wage increases as well. So that's certainly an indication of potential heteroskedasticity, and always a good idea to do that visual inspection. And since it's such a good idea and such a common post-estimation step, of course, Stata thinks of this as well, and it has this built-in RVP plot command, so residual versus predictor plot. And if we just type in RVP plot education being the predictor of interest in this case, it brings us the exact same plot. So we don't have to generate those scatter plots every time. So if you had 5 or 6 variables that were potential heteroskedasticity causal factors, we can cycle through those real quick just to get that visual inspection. The next kind of visual that you want to get is maybe a more direct representation of that error variance. And in the case of all of our testing, our proxy, our stand-in, our estimator for the individual observation error variance is simply going to be the squared residual itself. So that's a good step. Let's generate a new variable, call it u hat 2, which is those residuals that we just created, that we called u hat, squared observation by observation. And again, at this stage, we're just taking a look at it. So let's go ahead and do that scatter plot command yet again. But in this case, let's replace the u hats with their squared values. So here we're not looking for widening dispersion, we're looking for an actual relationship, right? So if we ran the regression here, we would expect to see a positive slope. It looks like as education increases, the average value of that squared residual increases. We can add that layer to our plot here, of course, easily. Instead, if we follow up in the same command line, the scatter combination, if we put in that linear fit, right, between u hat 2 and education, it'll overlay basically a simple regression line. And we see that positive slope, so it seems to indicate higher levels of education, higher average levels of squared residuals, which represents higher variance of our error terms. So everything seems to be pointing in the direction of heteroskedasticity, at least partially due to education. So that puts our regression results up here in a slightly new light, right? We now know that it's not going to cause bias in the coefficients, but the standard errors, the t-stats, the p-values are all going to be potentially incorrectly calculated if we suffer from heteroskedasticity. So we want to make sure that we know the answer to that question. So the next step after our simple visual inspection, we want to run a few statistical tests. We'll just look at 2 of them here today. There's, of course, a wide variety of tests available. But the 2 I like to do are the so-called Park test and the Breusch-Pagan test. Probably mispronouncing that last one. But let's go ahead and take a look at the Park test first. And what the Park test does is it picks out individual causal variables that may be predictors in the regression, may not be, and simply regresses them against a version of our error variance estimator, the squared residual, right? But in the Park test case, the default is that it's a log-log model, so we're assuming a non-linear heteroskedastic relationship. The beauty of this test is it gives you kind of real simple results. All you're looking for is whether or not that t-statistic is significant, and it also picks out, again, individual causal factors, so you can kind of tell where the most significant impact is going to be. What are the most, what am I trying to say? The variables that are most significant in causing heteroskedasticity, right? So to do this, we have to generate a new version of our residuals, so it's going to be the natural log. So let's generate L u hat 2, so the log of our squared residuals, just for the purposes of this test. And these are going to be, again, the natural log of our u hat 2. There we go. And then whatever we put on the right-hand side, that's going to be in log form as well, if it wasn't already. Again, that's just our default version of this test. So we're going to focus in on that education variable. So let's create the log of education. There we go. And we're going to go ahead and run just a simple regression. So log of our squared residuals as a function of our log predictor variable. And all we're looking for is this guy right here. So we do in fact have a positive coefficient that is significant at 1%. So that visual, right, of increasing education, widening this dispersion, increasing our error variance, that seems to be borne out in the test. So you would generally want to apply this to all of your suspected causal factors. But at this point, we're already sure that we have heteroskedasticity, and we know that education is at least one of the causal factors. Right? The other test that we would want to take a look at, that so-called Breusch-Pagan test, that's going to be more of a general approach, right? Rather than focusing in on one single predictor, we would put all of our x variables in the original model that we're predicting y, use them as predictors of our error variance, proxied by our squared residuals. And again, the default here is just to do it as a linear regression. So we would just do regress u hat 2, and then whatever was on the right-hand side of our original model, we're going to put it here as well. So it's going to be education, work experience, and our gender control, that female dummy variable. And here, instead of looking at the t statistics, even though in this case they are all individually significant, the focus would be on the f statistics. So we're just kind of getting that thumbs up or thumbs down. Is that combination of variables, are they jointly significant? If so, as we see in this case with an f-stat of 13, well beyond our 1% critical value, we can reject the null of homoskedasticity, right? If those coefficients were all insignificant, that would be consistent with a homoskedastic error term. It's not changing observation by observation. But here we can reject the null. A real nice feature of this Breusch-Pagan test, yet again, is Stata has a built-in command. Right? So if we go back and rerun our original model, I guess I should have just wrote it in at this point. So it's regressing wage against education experience and that female dummy variable. Post-estimation, the command here is just het test, one word, no spaces. And we're going to use two options here that are going to make it exactly replicate what we just did by hand. We're going to use the option RHS, so that includes all of our right-hand side variables, all of our x variables. And we're also going to ask Stata to do this with our f statistic, right? I can also do it with a chi-square test statistic, but to match what we see with the regression results and what we're more familiar with at this point, we'll use that f-stat command. And we get immediate feedback, right? We see just what we saw with our regression version. F statistic 13, highly significant, reject the null. This model definitely has heteroskedasticity. Now the question is, how do we fix it? So stay tuned. We'll do another short video on various methods of how to fix this problem. But as far as testing, this is enough to get us to the point where we can make a determination, yes or no. So thanks for watching, and we'll catch you on the next one.